Okay. Today's class actually won't be overly difficult. We're not really adding anything new. We're literally just going to be looking more applications of what we talked about last class. You will need the table, so pull that out. There might be a couple extra ones still over there if you lost one. If I run out, share, and I'll print more out for the next class. All right.
Did you see online? Did you watch it? It looks crazy, but it looks crazy, but it's just super helpful. So like basically you just like run out of the grid, like once you figure out the scores and stuff, like you'll go over here. And this is just 100, so you'll go over here and line up that.
If you don't have one, look on next. Your neighbor should have one. I'll have some printed out for the next class for Monday, because you're going to be able to use it on the test. So, yeah, for those that weren't here on Monday, it looks nuts, but it's really not that bad. All right. So let's start. The biggest difference between what we did on Monday and what we're doing today is you're really not going to be given the z-score. So you're going to have to find the z-score first and then plug it into the actual setup. So suppose the National Testing Service gives you a test, which the results are normally distributed with a mean of 400. So the SATs, this is literally actually how they do the SATs. So the SATs should, when they're designed, the mean score should be 400. So if you're average, you should get a 400 on the SATs. Standard deviation is 100, and it goes up to 800. So if you think about now, we're talking about if the mean score is 400 and the standard deviation is 100, what's the maximum standard deviation, or how many steps could we go? Since the maximum score on the SATs is 800. 4. So basically, yeah. So if you look at it, your table doesn't even go up to 4 for standard deviation. So it's a very, very small chance that anybody would get a 400 on the SATs. All right, or an 800 on the SATs, I should say. And that's works out to be right. Out of the millions of students who take the SATs every year, there's maybe a few thousand that actually get an 800 on either of the sections of the SATs. So, all right. So if you score a 644 on the test, what fractions of students did you taking the test exceeded your score? So 2 steps. First thing we have to do is figure out where we're looking on the actual chart, and then we'll find our z-score. So if this is 400, and we're going up to 644, so we're looking at kind of over into this area here. Are we looking above or below? Above, says exceeded, right? So we're looking at this little section over in here. All right, what was the z-score formula? Yes.
Was x minus the mean over standard deviation?
Yep. X minus the mean over the standard deviation. So in this case, my x is the score we're looking for, which is the 644. My mean is 400, and my standard deviation is 100. So 644 minus 400 divided by 100 gives you 2.44. When you're doing the chapter 8 on for the homework and stuff, throwing this formula into Desmos so you can just literally just change the numbers probably is going to be an amazing feature to do because you're going to do a ton of these problems that are very similar. All right, so we got 2.44 as my z-score. So let's look at the table and find the percent for 2.44. So reminder, the numbers up top here, those are your last digit. So the second digit after the decimal. So we're looking at the 4 there. And we're going to go down to 2.4. The 2.44 is 0.9927. Is everybody able to find? Oh, I don't know why I clicked on the. Is everybody able to find the 9927 there? All right. Is that my answer? No. Because with that is, remember, the table's showing you from the left all the way over to where you're looking for. So that is giving me the area over here. So what do we have to do with that number? 1 minus it. So 0.70073. So that is the percentage of students taking it that would have exceeded your score. Yes.
Can I ask for a fraction?
Oh, they're using fraction not as in the term of a fraction. They're targeting as a portion of the whole. Good question, though. If for some strange reason, if Hawks actually wanted it as a decimal, it'd be 73 out of 10,000 because you can't break down the 73 anyway. But I'm 99% sure that they meant the portion of the group, not necessarily a fraction. All right. So the big thing that I mentioned on Monday was drawing the picture and shading so this way you can see where you're looking for, because that's going to make it tremendously easier when you're trying to find the final answer. Yes.
Where did we get the 0.9927?
The table.
Oh, yeah.
So we looked up to 2.44. Actually, you know what? I want to do one more of those before I go on to the next one. Hold on a second. I'm going to get another one of those problems. Because I want you to try one. All right. Find the answer to this one.
Are you gonna put it up?
Oh,
Sorry, I'm still doing it.
sorry. What happens when I don't look backwards? Fine. So we should be, we were at 200 or 200,000, which is down here somewhere. We're not exactly sure where, and well, honestly, when you're making the graph, that's where that line is. As long as it's on the right side of the mean, doesn't really make a big difference on where it is. And we're looking for less, so that means we're looking for this section over here. So we need to find our Z. So 200,000 minus 100 or a million divided by 500,000. So negative 1.6. And since it's always, your Z-score is always to 2 decimal places. If there's no decimal places, put a 0 there. All right, so if we load to the table, yell at me if I don't switch back afterwards. We're looking at the negative side, and we're going to do negative 1.6, and the 0 is the first column. So negative 1.60 is 0.0548. So is that my answer? Yes, because remember, the table's telling me from the left over. So that is that answer, and that's the one we want. So that is the answer. If it wanted you as a percentage, just move the decimal 2 place. So that would be it as a percentage. Yes. If you got a number that was really high.
Oh, okay.
So like the biggest mistake that people are going to make on this is looking on the wrong side. So if you looked at 1.6 and you got 0.9452, like that just doesn't seem right for where you shaded.
Right. Okay.
So that's the concept of where you're looking at, like to figure out if it's wrong or not. It's like when we know it's down here, remember the breakdown of the table. So let me actually do this one real quick for the ones that were not here. Nope, wrong one. So if you remember, each side's 50%. So that's 50%, and that's 50%. When we're looking at this box in here, that's 68% or 34 in each one, approximately. When we're going out one more, that's the 95%. So we have another 13% basically in each side there. And then when we go out the furthest one, we get the 99.7. So when you're looking at it, it's like, okay, I know it's somewhere over in here, so it's not going to be that big of a number. So it's like, that's why the shading and the coloring kind of helps. It's like, okay, I know it's a very small section, so it can't be that big of a number. So that's where you're looking at the mistakes. And honestly, the biggest mistake you're going to make is just doing the opposite number. Yeah.
One, you subtracted from one. Is that just because the problem was working?
Yeah. So this one, we wanted this side over here. So in the table is always giving you from here over.
It's the complement.
Yeah. So in that case, it's the complement of it. So if you're looking for the right side of the graph, basically, that's where you're going to actually do that 1 minus. When you're looking at the left side, the table tells you that answer. So like in this question, if it asked what portion of the firms earned more than ARC, I'd have been looking at this section over here, and then I would have done the 1 minus it to get that answer. Yes.
Does the graph need to be accurate, or does it just have to hit the point?
The graph doesn't have to be accurate at all.
Okay.
Honestly, the biggest piece that you're looking at is making sure you're on the right side of the mean. That part's important. Other than that, like we were at 1.6, I was pretty close to the line here. But like on this one here, we were at like, it was 2.44, and it's like, I could have literally put it there and it wouldn't have made that big of a difference. Because the concept that we were getting at is the same. I'm still looking at that little piece over there. Yeah, it's just to get you to make sure you do like this. Oh, I have to subtract from 1. I don't have to subtract from 1. That answer makes sense. Like the chances of you screwing up, like I guess the only other big thing would be screwing up like the 0 and thinking this was 1. And unfortunately that one, you're just, because the numbers are going to be so close, you're going to get it wrong no matter what. If you make a mistake on this, your mistake's typically going to give you an answer that's way off from what it should be. It's not going to be very, very close. So, all right. Next one. So this one, we kind of did one similar to this one in class on Monday, but it's always good to refresh our memory on some of these. This is going backwards. So we want to know what the variable x is. So in this case, I don't know x. I'm looking for x. But I know my mean is 28. I know my standard deviation is 2.5. And we're going to have to find my z to go backwards and find the x. So this one we have to do a little bit of algebra. All right. So they want an area to its right equal to 6.67. So is my line going to be on the left side of the mean or on the right side of the mean? If I want an area on the right of 0.67, so from a line that way, it's going to be 0.67. So each side is going to be a half, right? So that means my line is going to be somewhere over here. Okay. Why is that important? Well, because that means that we're looking for a negative number. So now this is 0.67, right? So and my table is always going to show me from the left. So what number is over here? So how much is left if I have 0.67 on this side of the line? The whole graph has to equal what? 1. So it's 1 minus 0.67. 0.33. So that's the number I'm going to look for in my table. Everybody understand why I'm looking for the 0.33? No isn't a correct answer. Like, it's fine. Okay. So the question wants to know, I want to know what the value of X is at this point. That's what I'm looking for. It told me that to the right of it, so on this side, is 0.67. So I mean 67% on that side. Remember, the table's always telling me from the left. So I can't look in the table for 0.67 because that's not on the left. I need what's on the left side. So if 0.67 is on the left side, 0.33 has to be on the right side because that has to add to 1. So I did 1 minus the 0.67 to get the 0.33. Okay? Okay. Now, to the table. Am I looking for 0.33 out here? Is that a Z or is that a percent or probability? That 0.33. That's a percentage. That's not a Z. Right. So on my table, I'm not looking on the outside. I'm looking on the inside in here. Correct. I'm looking for where it equals 0.33. So I'm going to actually, so I can write on this. So we're looking, so let me just put the numbers up here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So we're looking for 0.33. All right, yeah, which is right there. Correct. Correct. You are right. That's the answer. What I was looking for. Remember, so we're looking at the percent, not the Z-score. I want the Z-score. In this case, we're working backwards. So in all the rest of the problems we've done, we had the Z-score and we were finding that number. This one's going backwards, which, yes, is sometimes a lot more complicated. So 0.33 is right there, which, as she just said, is negative 0.44. That's my Z-score. Okay. Did everybody find 0.33 on their table? If the number wasn't there, you're looking for the number closest to it. So this one was exactly there, so we're good. If it wasn't, we would want the closest one to that number. Okay. It's not Price is Right rules. It's whichever one's closest. Yes. Okay. So, well, the nice thing is, on this case, the table shows you that. So if you look at your table, on the positive side, they start off at 0.5. So since I'm looking for 0.33, I can't look on the positive side. So so remember, the graph splits. It's 50% on one side, 50% on the other one. The middle is 50%. So that kind of gives you the direction you're going on it. The mistake would have happened is if you look for 0.67, which would have actually given you the positive 0.44. And that's why we drew the line and figured out where it was going to be. So I knew that I'm looking for the negative version of it and not the positive version. So that helps. That's why the picture helps a ton when you're looking at these. All right, so I know my Z is negative 0.44. Okay, so let's plug in my formula, and we'll remember the formula. So I know this is negative 0.44 equals X minus 28 over 2.5. This will probably be the extent of the algebra you're going to do in this class. Okay. Does anybody remember how to solve an equation? Yes. Yes. Correct. Let's get rid of the 2.5 first. So 2.5 times the negative 0.44 equals x minus 28. Which gives you 1.1 or negative 1. And then how do I get rid of the minus 28? Add it. So I get 26.9 equals x. And that's my answer. I'll go back one thing. Yeah, makes sense to say that. All right. Why would we care about that? Why would we care about this process? Think about one of the concepts we talked about before is when you go to the doctor's office and tell you, oh, your baby's in the 95th percentile or 90th percentile, things like that. Well, you can use that to find those numbers. So like this problem. Your normal body temperature is 98.6. What temperature represents the 90th percentile? Okay, so what's 90th percentile mean? How do we change that to a number that I can use? 0.9. Okay, so that right there, remember, it's just a percent. So that's the same thing as saying 0.9. That's the same thing as saying that. So I'll mark down the things that we know. We're looking for the x. We know my mean is 98.6. My standard deviation is 0.73. We don't know my z yet. We have to find that. Which side of the graph is the 90 going to be on? Left or right? So it's going to be somewhere over here, right? And then that means in this, that's the 0.900, right? Okay, is that the number I'm looking for, or do I have to do the 1 minus it? Yes. That's what I'm looking for, because remember, it starts at the left and goes over. All right, so take that and go backwards and find my x. 6.90. Switch back and forth. All right, you should have gotten 99.5. So in this case, the 0.9, the 90% was not on the sheet. So the numbers go in order, so it kind of makes it a little bit easy to scroll down. The 0.9 is not on the sheet, so you have 0.8997 and 0.9015. The 0.8997 is closer. So that's the one I would take, which is 1.28. So solve my problem, and we get 99.5. All right. Does anybody remember the horrible days of COVID when they had to scan your forehead to determine if you could come into the building? Does anybody remember what the temperature they would yell at you for is? Actually, it was exactly 100. Get a temperature of 100 or more, they'd send you away.
My brother runs pod.
Yeah.
Every time they thought like, oh, you can't come.
Well, that's literally what I was going to say. We just found out that 10% of the entire population has a temperature higher than 99.5. And if we actually did it for 100, it's actually like not much higher. It's like 95. It's like maybe about 5% of the population actually has a temperature higher than 100 as a normal body temperature. So it was like, you have to know your temperature to determine like what you consider a fever. If you typically run hot, if you're a little hotter than that, that's not that big of a deal. That's normal. The other thing we got to look at is that on the opposite side of things, you have people that run really, really low. So if their normal body temperature is like 97, if they're at 100, that's really bad. So we assume when we hear, oh, the average is 98.6, that everybody's there. That's not the way percentages work. You have a range. So, and those machines were horrible that they were using. Was like they scanned me, like you come outside when it's really cold, they scan you like 95. Okay, I'm dead. Yes.
The opposite happened to me. I used to work at Chipotle and it was like really hot outside and my AC was out and I lived 5 minutes from Chipotle. I'm from Ohio.
Yeah, it was like you'd run in and it's like,
And I went inside and they scanned me and I saw the thing flash red and they were like, sit down, you can't work. And so I had to sit.
and wait to cool off.
Yeah, and they scanned me again. I was like, oh, you're fine now. I'm like,
It's like, I'm fine. I'm just hot. It's hot outside. Yep, it happens. So that's the thing. When you're looking at it, you always have that range. You never have the exact set number. I actually think that was the problem that I was going to do that one on. Let's complete that one because I already did. All right. Yes, I know it's VJT monitors, which are really old now, but the concept still holds. So, has anybody ever bought something and it died like right after your extended warranty goes out, or your warranty? That's on purpose. And it has nothing to do with them trying to sell you more. They chose that number because they know that's when they will start to fail. They do studies to figure that number out. Okay. And they know that whatever number they set, they expect a certain percentage of them will fail prior to that time. Okay. That happens. All right. So VGA monitors manufactured by this company has a lifespan of 15,000 hours at a standard deviation of 2,000 hours. What is the probability that the lifespan of the monitor will be less than 12,000 hours? You're up. You should be able to do this. This one's not a backwards problem. So 12,000 hours is going to be on the right or left side. And we're looking for less than that. So we're looking for there. So X is 12,000. And it's 15,000. Standard deviation is 2,000. And now we need our Z.
The
Yes.
area you shaded is for A, right?
Yes. Yeah, we're just doing A. This is A. So what's my Z? I get a 1.5. All right. So look that up in the table. And we get 0.0668, I think it was. I keep having to go back. 668. So 6.68% of the TVs will fail prior to 12,000 hours. So I'll set my warranty for 12,000 hours. And in that situation, I'll have to pay out 6% of the TVs that I sent out, but everybody else will be shit out of luck. So you get a 16-month warranty. Or maybe we'll just do it down and we'll say 15-month warranty. Why would they say 15 months and not 12,000 hours? Because I don't know how long you're leaving the TV on for. But 15 months is if you leave it on 24 hours a day. Which you're probably not going to do. But that saves me the work. So this is how they actually come up with these numbers. Yeah. Look at the very top. Those are your last digits. So 1.50 in this case. So that's why we're choosing that one. So like in the last one, we had 1.28, 1.2, and it's the 8th column over. Or actually the 9th column because the 0 is the first one. So now you know why everything always seems to fail right after your warranty expires. All right. We also talked about, not this week, last or before break, we talked about another type of distribution or another type of experiment. Yes.
Sorry, were we not doing the last?
Oh, I'm not going to do the other two.
Oh, okay.
So we talked about a binomial experiment. What's the key with a binomial experiment? Well, what makes a binomial thing special? Yes.
There are two modes, right?
Correct. No, there's not two modes. That's bimodal.
Oh, my bad.
But it does have something to do with two.
Yeah.
Yes.
Like two things going on at once. Like, kind of like.
Give me an example of that. Yeah, it's success or failure. We have two options, two possible outcomes. Success, failure. Okay? Those are the only two possible outcomes. The nice thing about when we're looking at a binomial, we're easy to calculate. Okay, so we have to be able to calculate these two things. When you're looking at problems that are dealing with a binomial distribution, you're typically not going to be given your mean and your standard deviation. They're going to give you the number of values we're looking at and the probability of success. Okay, so that P is not what we're going to be looking at the table for. That's the probability of success. Okay. So for this, N is 20 and P is 0.5. So those are the two values that they're going to give you. We now need to find my mean and my standard deviation. So mean, do that in a second. Interesting. Can't erase. There we go. Is going to be 20 times 0.5, which is what? 10. So my mean is 10. My standard deviation will be the square root of 20 times 0.5 times 1 minus 0.5. First time I need to actually open up Desmos now. And we get 2.236. So that's my standard deviation. Okay. Remember doing that? That's from like chapter 7, I think it was. Might have been chapter 6. All right, so we've got those. Now we have to do our new steps. So the first one, A, says, I want a probability that the binomial random variable is 5 or less. Okay. So in this problem, when we're looking at binomials, binomials are they discrete or continuous? When we're looking at the distributions. They're discrete, which means, and this graph is continuous. Okay. So typically when we're looking at a binomial distribution, we're looking at something that looks like this. This is what it would look like. So histogram of values. And they each have their percentages. But what does that look like if I was to draw a line over it? Looks like my bell curve. But the bell curve is continuous, and this is discrete. We're going to be able to estimate using the bell curve, so I can use all the stuff that we just talked about, the wonderful table and everything else, and we don't have to do all these calculations. However, we have to make one minor change. Because it's continuous, I can't use exactly 5. So depending on which direction you're going and depending on where you're looking at, we have to do the +5 or -0.5. Okay? So in this case, since I'm looking for x is less than or equal to 5, I'm going to make my x for my problem 5.5. Okay? Okay. So A, let me erase B for a second. So A is just looking at, it says the variable is going to be is 5 or less, which means x is less than or equal to 5. Because I can have 5 and everything below, right? That part makes sense? Okay. So because this is discrete, and I'm doing it on a continuous table, I can't plug in exactly 5 because it's not going to give me 5. It's going to give me the values below 5. So I technically could do any number I want. The standard rule is 0.5. So I'm going to make x equal to 5.5 for my problem instead of 5. I'm always going to go up by half or down by half, depending on which direction we're looking. So for my problem that I'm going to do now, when we're looking at the steps, okay, so when we're looking at the steps for this, I'm going to use x equals 5.5. My mean is 10, and my standard deviation is 2.236. Now, where's that line going to go? On the right side or the left side of the graph? The left, because my mean is 10, right? So that means it's going to be somewhere over here. And we're looking for less, so we're looking for that area there. All right, so find me my z-score. So what do we get?
Negative 2.01.
Yeah. Does that number make sense for your Z? It's negative. It's not really close to 10. All right, 5.5 is a little way away from 10. So, yeah, that number kind of makes sense. Okay. So now I can look at my Z table for negative 2.01. And I get 0.0222. That's my answer. Because I'm looking at the left, I don't have to do subtraction or anything else like that because it said less than.
Sorry, can you go back for a second?
Yeah. All right. Now let's try a regular one then. Yeah, let's do this one. The hardest part of the test in any of these problems is going to be figuring out what type of problem it is to start. We've done two different types of normal distributions. We've done the binomial one and we've done the regular one. The biggest difference between them is the binomial one is not going to give you standard deviation and mean. Okay, so if you're looking at a problem and it does not give you those two things, it is going to be a binomial problem and you have to find those two things. If it gives it to you, we don't need to find them. We can do the other one.
Which
Standard deviation and mean. Because in a binomial distribution or the binomial experiment, we can calculate those, so they won't give them to you. All right, so they've done this study and they want to know how many people are aware of the new campaign. Yes.
sorry, and the inverse would be
They give them to you, so you don't have to find them. So you can just do the standard method.
but you'd be finding what the probability.
You're still always going to be either finding the probability or finding X, or depending on what they're asking. So you either have to calculate the mean and the standard deviation or you don't.
Okay.
Everything after that point is actually the same process.
And it's the binomial that gives them is the standard deviation.
No, the binomial doesn't.
Doesn't.
Yes, it does not give you the standard. Like the one I'm about to do. All right, so upon completion of the new campaign, the agency claimed 20% of the alumni and the state were aware of the new campaign. So is this a binomial experiment? Yeah, they're either aware or they're not aware. There's nothing in between. Okay, so this is binomial. We're given the probability, so the P is 0.20. So they surveyed the agency and of 1,000 people. So my N is 1,000. And they found 150 were aware of the campaign. Okay. assuming this is true, what is the probability that no more than 150 of the alumni in the random sample were aware of the campaign? So my X and they want no more than 150. So am I going to use 150? Am I going to use 150.5 or 149.5? I want more, so no more than 150. So that's less than or equal to 150, right? The less than or equal to means I need to go up a little bit. So I'm going to make this the 150.5. I need to go up just by a little bit. So that includes the 150. All right, let's find the mean so we can figure out where I'm going on this one. What was the formula to calculate mean? N times P. So 0.2 times 1,000 is 200. So that's 200 right in the middle. So 150 is going to be somewhere over here. Yes.
The probability part, how would you write that out? Like it's usually with the less than, like it says no more than this many, so it'd be
Oh, so it'd be
X
is less than or equal to.
less.
No more than is less than or equal to. So that means the less than or equal to is over in this area over here. That's where I'm looking at. What was the formula for standard deviation? It was N times P times 1 minus P. So I got 12.650. Oh no, sorry, 649. So let's find my Z. This is literally how I'm doing it. So my Z is negative 3.91. All right, look up. What's it?
No, you.
What is the percent of negative 3.91? Good. So it's a really, really small number. Hold on 1 second. All right, what was your question? Sorry.
I was gonna ask, will we get questions that go that high?
So you could. I think in Hawks, they probably would give you the table that went that high.
Yeah.
However, in most situations, like in this case, it's 0.0001. It's like a really small number. So the question is their claim correct? If their claim that 20% of everybody found it, they should get close to 200, right? We only got 150 people. So, and the chances of that happening is almost nothing, which means their claim is probably wrong. What we're going to be going into next, after the test next week, is that's what we're going to be looking at. That's actually the true end of statistics, is when we start doing hypothesis testing. It's taking what we're doing now, in essence, it's exactly the same concept, and looking at the number and comparing it to something else and going, wait, this number makes no sense. It's way too low, so therefore the claim is wrong. Okay? So we can say we will reject their claim or reject the hypothesis, is what we'll in essence do, because that just doesn't make sense. The chances of that happening is next to nothing. Now you can see why, like, where I put the line doesn't really matter, because that line is nowhere close to where it should have been. Okay. All right. We're done. The review for the test should be online, Hawks? Yes. Yeah.